All right, guys, Math 6620, more on regression. What I want to do here is I want to use a data set that we used in a previous video called exam anxiety. Remember, it's an SPSS format, so we'll have to convert that using a package called foreign. But what I want to do is I want to just kind of implement some of the things, techniques, terms, sum of squares, those types of things for simple linear regression on a real life data set. And then I want to transition into multiple regression and use not only anxiety to predict exam score, but to use gender and anxiety. Now, there's no real reason here for me to think that there's any sort of gender issue, but you know, it certainly doesn't help to hurt. It certainly doesn't help to hurt. Who's talking here? And again, it makes a nice transition into multiple regression. All right, and comparing the two, we can look at AICs and different things. So, guys, let's do it. Let's get out of here. I'm just going to close that down. You can see that I have exam anxiety on my desktop. So let me open up R. You know, I have a lot of students that ask me, and they're like, Dr. Darver, why don't you use RStudio? It's so much easier. I don't know. I don't want to. So leave me alone. Okay. All right. So I want to, well, first of all, let's, all right. So data. So I want to do read.spss. And I want to get my data set. But I have to do a little trick here. To data frame equal true to get this in the format that I need. Now, we get an error. I'm not really sure what the warning is. It's really not, it's an unrecognized record type 7, subtype 18. Guys, I don't know what this is. But if, and again, this is just an academic illustration, but if, you know, if this was data that I was using to publish and, you know, make decisions about people, maybe to create policy, I'd want to look into that a little bit more. But for right now, I'm just going to proceed. And I want to look at my data, make sure nothing wacky is going on, and we can see that we have what we need. So I don't see any missing data, but so anyway, all right, let's go for it. Now, what I like to do is I like to get the names of the data because, again, capitalization matters, and to you and me, uppercase, lowercase exam is just exam, but to R, it's like Venus and Mars. So, so let's create our model. So our model, first thing I want to do is I want to do a linear model of exam score. From anxiety only. And then I want to look at the ANOVA like we did before, and we can see that our sum of squares are extremely large. However, I noticed right off the bat that my residual sum of squares is about 4 to 5 times what my anxiety. So that tells me my R square is going to be low, and I'll calculate that in just a second. But when I come on out to the F value and the probability, I see that my model is statistically significant at the lowest level, the 0.001 level. Now, I know that my R squared is going to be equal to my sum of squares for the model, which in this case is 13,348.2 divided by the sum of squares for the total. So to get that, I have to go 1348.2 plus the sum of squares for the error, which is the same thing as sum of squares for the regression, or residuals, I'm sorry. So R squared is 19.4%. So we can say the 19.4% of the variation in exam can be explained by the regression on anxiety. All right, so our model is statistically significant, again, meaning that using anxiety to predict exam is better than just using the mean for exam. Now, the next thing I'd want to introduce into teaching you this technique called regression is to look at a summary of the model. Now, this brings in kind of a different, something else kind of different to look at. And this focuses on not the overall model, but the individual coefficients. Now, when we got a single predictor model like we do here, you can see that our ANOVA table and our predictor give us the same value. The reason is because the t-distribution squared is the f distribution. So guys, if I take negative 4.938 and square that, I will always get my f value from my ANOVA, and that's the reason that it produces the same p-value. But when I look at this, I typically start from the bottom, and you can see from the bottom it gives us our overall f statistic, which we got from our ANOVA model before using the sum of squares from the previous video. You can see that we get a multiple r squared. That should look really familiar to what I calculated right back here, because it is. When we only have one predictor, we can calculate, well, it doesn't matter how many predictors we have, we can calculate r squared by taking the sum of squares for the model divided by the sum of squares for the total. The adjusted r squared would only be applicable here if we have multiple predictors. Now, the residual standard error, this is a measurement kind of on the variance of our residuals. But what gets my attention in this output is the information on anxiety. Now, first of all, this estimate tells us kind of the nuts and bolts of the impact on anxiety, the impact on exam from anxiety. So what I can say here, it's a standard definition of a predictor when we only have one predictor. It deviates a little bit, changes a little bit when we have multiple predictors. But when we have a sole predictor, we can say that as anxiety score increases 1 unit, as blah, 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 anything, whatever our predictor is, whatever our independent variable is, as it increases 1 unit, the change in the predicted y, which in this case is exam, is precisely the number you see right there as your estimate. So, not stumbling through it, I'm going to give you a formal definition. As anxiety score increases 1 unit, the predicted exam score decreases by 0.67 units. This predictor is statistically significant at the 0.001 level. Now, we're going to get into deviances in different ways to analyze the the fit of our model. But the thing I look for up here is I kind of look for symmetry. In other words, I want the minimum value, which is always going to be a negative, and the maximum value, which is always going to be a positive, to kind of balance out 42 and 49, sort of. I want my first quartile and third quartile to be similar, and I like my median to be somewhere around 0. But we're going to get into a lot more scientific stuff later on, other than just eyeballing the 5-number summary for the residuals. Now, what I'd like to do next is I'd like to move into the next model, and the next model is going to bring in gender. But I have a problem here. I have a problem with the way that R works. I'm not sure what it's going to use as its base. If you read about R, it typically says that the first subject is going to be whatever the gender is in this case. It's going to be the base. So it's going to have your base gender as male, so it's going to compare females to male. If this first gender was female, it would be the base, so our coefficient of the model would compare females to males. So to me, that's kind of confusing. And I don't want a machine making that determination for me. I want, based on some scientific, some research interest of mine, what I want to compare to. So maybe I want to see if males are outperforming females, in which case I want to set females as my baseline. So if I want to set females as my baseline, I'm going to do a gen recode. and I want to do an if-else. So if gender equals female, I want that to be set as a 0, otherwise I want it to be set as a 1. So because my females are going to be 0, they're going to be the base in the in the coefficient, my estimate. So I'm going to be comparing males to females. This is going to be really important when we get into things called dummy variables, where we have categorical variables with more than 2 output. All right, so now what I want to do is I want to go back up and to where I did my model. Guys, I'm going to change this and call it my second model. And I want to add gender code. All right, first thing I want to do is I want to look at my ANOVA for model 2. And there, you know, we get, obviously we get our, it's interesting. Typically, and guys, I'll get this worked out, there's a way that we can just get, what R does, and I hate that they do this, but there is a way that we can change this, and I think I may remember how. Let me see if I can, and I may have to look this up. Yeah. So anyway, guys, I will, I don't like the way this does it. I like for the anxiety and gender code, which are my 2 predictors, I want this to all be on one line and give me one F value and one sum of squares and one P value. But for some reason, I remember R doesn't do that. So guys, I'll get that worked out. I don't remember how to do that right now. I usually just kind of shoot from the hip when I'm creating these. But we can get the overall model fit using summary model. And if we go down to the very bottom, the F statistic will tell us that our total F statistic is 12.07, degrees of freedom 2 in 100, and our p-value, you can see, is statistically significant at the 0.001 level. Now in this case, we would want to concentrate on the adjusted R squared instead of the multiple R squared, because we have more than one predictor. So we would say, using the adjusted R squared, that 17.8% of the variance in exam is explained by the regression on anxiety and gender. Now, when I go to gender, if I don't know how my gender is coded, then that 0.295 doesn't mean much to me. But because I know the way that I coded this, and I set female as 0, so think about it. As I increase 1 unit, what am I doing? I'm jumping from females to males, because females are 0, males are 1. So I can say that controlling for anxiety, males are, the exam score for males is predicted to be 0.295 higher than for females. Now, if I had just done this, let's do a model 2, and instead of, let me get that out of the way, let's just go in and do gender, and do summary model 2, and you know what's going to happen. It's going to give us to the reverse way. So what happened there, it appears that what they say is whatever the first gender, whatever the first value is in our categorical dichotomous variable in this case, that uses it as the base. So that does make sense in this situation. But I'm a little freaky about this stuff. I want to have control, and it actually tells you there the comparison. Now this is actually comparing females to males. Where up here I did a comparison of males to females. I like to have control of that, and this if-else allows me to use numbers and gives me control of that. So again, gender anxiety. Notice it didn't change much. Gender is not statistically reliable. So we have a question now: does including gender do any good? Does it help us at all over just using anxiety? So what I would like to do is I would like to look at my AIC for a model, and then I'd like to look at my AIC for the model 2. And as you can see what happened, remember the lower value indicates a stronger model, stouter model, better model. Worst, as I said so embarrassingly in a video. You can tell I'm not full of myself, otherwise I would have redone the video for something goofy like that. But the AIC is lower for the model with just anxiety, so really by including gender in my model, I really haven't accomplished much.